I'm going to plug this into the original differential equations, and then calculate what the orders of these polynomials are going to be like.
Perhaps that's what they propose, like the singular solution. I mean, they propose that this has this form.
Yeah. Yeah, this is a very well-established expression series in maths already. In applied math, they just
propose. So, I mean, it's not a general solution, but some proposal.
Yeah, this is a general solution proposal for it.
Like a trial solution.
Yeah, it's a trial solution. Yeah. And now I'm going to do the maths. That is our first solution, trial solution, which I have written in condensed form instead of writing everything else because of space to write everything else out. X, Y, Z. And this is our differential equation system. If I plug x into that differential equation, I would get this. So P prime, sorry, dangerous. P prime means P dP by dt. I use prime to denote differential with respect to time. So when you differentiate the first term first, and then leave the second term out, and then differentiate the second term, and then leave the first term untouched. That's the left-hand side. The right-hand side is easy. You just say 10 times y, which you put down there, minus 10 times x, which is that and that, which you, sorry, 10 times x should be that one, right? Well, this two things is y, and that one thing is x. So do the same thing to the second differential equation, third differential equation, you would get this and that.
It's actually the one right-hand side is both y and x, but you just pull out the n minus 2 term.
Yeah, yes, that's right. I just put this out. Because I want to write this in a compact form, I could have written this separately to make it conceptually clearer. This is not conceptually clearer, but it is cleaner, just the form is cleaner, because you can put these two in nice brackets. How do you solve it? So, I've reproduced the equations here. I'm not going to prove it, I'm just going to state that terms with same order are going to equate. So if you take this to be minus 2, for example, if I take m to be minus 1 and plug it in, this term to be minus 2, and that term, and that term, and when this is equal to minus 2, they're going to equate, and all other terms are just going to disappear. And I'm not going to prove this to you because it's quite mathematical. So first of all, I take m to be minus 1 and see what happens, and plug it in there. So this is minus 1, right? Corresponds to that. And that m is minus 1, which is a minus sign there. That is minus 1 there. That term is left here, which is 10 cubed minus 2, and then this cancels with that, with both minus 2 on the top. And if you do the same, when you take m is equal to minus 2 to this equation, you get that. Do the same to with m is equal to minus 2 to this third equation, you get that. And the paper says, which I don't completely understand, I hope that some of you can point it out to me why this is the case. It says that the degree of p minus 1 and q minus 2 must be the same. And the degree of p minus 1 and q minus 2 in eta must be the same. Eta is the argument of the variables. And the degree of r minus 2 must be twice the degree of p minus 1 and q minus 2. And then the degree of q minus 2 must be the sum of the degree of p minus 2 and r minus 2. They just stated that, I don't know why.
Hold on, what was the question?
Doesn't it come from the solution?
No, it doesn't come from solution. I don't know where it comes from. You say the degree of that and that. The degree of that and that is the same. The degree of r minus 2 must be twice this one's degree and this one's degree. And the degree of q minus 2 must be the sum of the degree of p minus 2 and r minus 2.
That's p minus 1 and p minus 2? I mean, no.
No.
Q minus... What does it mean? I don't remember.
The degree...
What is p minus 1?
Well, p minus 1 is just a...
It's just the minus 1 filament.
This thing, right? P minus 1 is this one, m is equal to minus 1. It is a polynomial
So I
in
should
eta.
So you said all other terms disappeared. So this polynomial now consists only of this p minus 1 term.
That's because I've taken m is equal... I've taken m to be minus 1.
Mm-hmm.
I've taken m to be minus 1, and that is minus 2, that is minus 2. All other terms that are not minus, that whose powers are not minus 2, I discard them.
But you could take 0 and then
I can take
some other
0.
solutions.
Next, this is the first step. Next step, I'm going to take m is equal to 0, and then m is equal to 1, 2, 3 to build up the whole solution.
Okay, so to your question, I think from the first equation,
Mm-hmm.
like if they are supposed to be equal, then they have to be the same degree. If that's p minus 1 and q minus 2.
Yeah. Well,
So they have to
can
be
you
the same
explain
degree.
why? That's fine. But why r minus 2 must be twice the degree of that?
And
and that?
here, if q minus 2 is the same degree of p minus 1,
Mm-hmm.
oops.
You
So
should
r
add
minus
r
2.
has to be twice the degree of what?
R must be twice the degree of that, or twice the degree of that, because they're the same, so it's the same thing. R must be twice the degree of that, or R must be twice the degree of that. In eta.
And
it's-
what is prime? Is it just
Prime is differentiation with respect to time. Here, right? Remember when you plug it in dx by dt,
Mhm.
that's where this term comes from.
Okay.
But it's not really a very crucial point. Let's just move on. This is not really important. So we just said that these two must have the same degree, that must have twice the degree of these two, and that must have, the degree of that one must be the sum of the degree of P and R. And those are all, those three are contradictory. It's impossible unless...
I mean, surely Q has to have the sum of degrees of P and R, because
Yeah.
if you multiply P and R,
Oh,
you're gonna
yeah.
have the degree of...
This is true.
Yeah.
This must have the sum of
It's
that.
like powers. P to the power of n and R to
Yeah.
the power of n.
No,
But
it's
from
not
the first
p.
one, it follows that p has the same degree as q.
P eta, for example, this thing could be eta to the power of 5 plus eta to the power of 4, ab, etc., etc. Degree means 5 in this case. There's the degree in eta, not p to the power of anything, it's eta to the power of something.
Okay, but in your P to the minus 1, eta is to the power of...
No, you don't know. You have no idea what it is. You're solving it to find out what it is. So this is not degree, by the way, this is just a notation saying this is the minus
yeah,
1.
it's
So,
minus 1 to the...
yeah. It doesn't matter. So we'll just say the three rules, but the three rules are contradictory to each other. It's impossible for this one to be twice as big as those, for those one to be the same, and that one to be that plus that. It's impossible. The only exception is when all of them have degree 0. So all of them have degree 0, and we solve this equation system, which is very easy, right? And the result is this. If you plug it in, you find out this is right, and it's just one solution. The other solution is
So that's what they said, it's impossible to have this.
yeah, they say the only possibility is for all the degrees to be 0. That's their original sentence. And we get this. Now we move on. We take m to be 0 and we get another equation.
So I know where this comes from, that r has to have twice the degree of p and q from the third one. Because right hand side has twice the degree of p and q.
You mean this has twice the degree of what?
R, you said that r has to have twice the degree of p and q.
Yeah, R has
So
twice the
that
degree
follows
of
from the third one, because
from the third one. Oh, that's true. Yeah, you're right. That was
What are the other conditions? Could you write them on the whiteboard?
That's
Please.
absolutely. So easy. I think Chris is
and that's
absolutely
the
right.
not,
Yeah.
not theta.
So p minus 1
Yeah, that's easier.
q minus 2 is equal. This equal doesn't mean that actually doesn't mean the degree is equal.
Mm.
And then q minus 2 is equal to p minus 1 plus r minus 2. R minus 2 is equal to p minus 1 plus Yeah, U minus 2. This is very apparent, right? Chris just pointed this out. Those two must be equal from the fact that these are in the same position, and Q must be that plus that because these two are multiplied together. Same with the third. And
Yeah, so it's quite obvious.
yeah, that's impossible because you just can't have to solve that unless they're all 0. So we assume that they're all 0. And then you solve this differential equation, saying that eta doesn't appear in this, and you get.
Well, it's impossible just because if you subtract the second from the third, you get Q minus R equals R minus Q, which can be true only if they are both 0.
Yeah, that's right. 2. So now they're all two sets of constants. And then you move on, take m is equal to 0. This m is equal to minus 1, this m is equal to minus 1, and you get another set of equations, which is this set of equations. Again, if you take the argument of degrees, you would see that the degrees must all be 0 again. And the solution is that. This time you only have one solution, not two sets of solutions. You just carry on and on and on. You would get an expression like this. This x is just a vector, and A is a matrix, X is a vector, F is a matrix. And what are they? They're this. X is equal to P, Q, and R. A is that matrix, and F is, this is a vector, even though it looks like a matrix. What we're going to do now is, because this is a rather nasty looking expression, we're going to diagonalize this matrix using the eigenvalues and eigenvectors.
So this is an analog of equations like we got here.
No, this is a general expression for m is equal to anything.
So these are the solutions? Or
Are they solutions?
Yeah, the plugged in solutions from the first solution, aren't they?
I think you have moved from different from that quite complicated summing equations to each individual equations without sums in it. That's what you have done now, but you haven't quite reached the solution yet.
so what is this?
Well, actually, sorry, I think you might have reached the solution already. So in this case, you have got the value for p to the power of minus 1. Sorry, not to the power. P sub.
So here you're showing some special cases for m equals minus 1 and 0, and that's what you've shown is for general m.
That's for general, yes, for general
okay.
m. Well, this probably is the solution. So if you plug this back into your expression, you will
Yeah.
get the psi series, and then that's the solution. And then if you use the diagonal matrix and eigenvalue and eigenmatrix to diagonalize an, you would get nice linear expressions like that instead of a vector expression. That 3 lots of that is equivalent to this if you diagonalize using this. These are eigenvalues of this horrible matrix, and those are just the variables, right? It's just the new variables. What we do now is we break this down into 2 separate conditions. One condition is when alpha is not equal to 0. The only situation when alpha is not equal to 0 is when m is not equal to 2 and 0, right? When m is equal to 0, alpha is equal to 0. When m is equal to 2, alpha is equal to 0. M cannot be minus 3 because it's impossible to get minus 3. If alpha is not equal to 0, we have a unique polynomial solution for eta, that's a xi. Unique polynomial solution for xi, whose degree is the same as that of f. However, we're not interested in that because, as I pointed out from the beginning, we're interested in singular solutions, singularities. So we want alpha to be equal to 0, which is either m is equal to 2